Hello all. This lecture is about traveling salesman problem using branch and bound technique. So earlier we had discussed various algorithm design paradigms such as divide and conquer, backtracking, dynamic programming, and branch and bound is one such algorithm design paradigm which mainly focuses on optimization problems. So here the given a graph, the objective of traveling salesman problem is to start from one vertex and then visit each and every other vertices once and come back to the starting vertex so that the sum of the cost to visit all these vertices is minimum. If there are n nodes in a graph, there must be n minus 1 factorial feasible solutions. And among those solutions, finding the best path is a traveling salesman problem. So here we define the graph using vertices and edges in case of directed graph, and it is represented by its edge cost adjacency matrix. So the edges are represented as I comma j, and the cost of I comma j is always greater than 0, and we set cost of I comma j is equal to infinity if there is no edge from vertex I to vertex j. Also, the distance between a node and itself is said to be infinity. Consider this graph. So its corresponding cost adjacency matrix is given here. So the cost from vertex 1 to vertex 2 is 10. So from vertex 1 to vertex 2 is 10, vertex 1 to 3 is 8, and so on. And the cost from 1 to 1 to itself is said to be infinity. The same way 2 to 2 is infinity, 3 to 3 is infinity, 4 to 4 is infinity, and 5 to 5 is infinity, and all other remaining costs are filled in its corresponding index positions. So we will be considering this. So consider this directed graph and its corresponding adjacency matrix is given here. So the first step in traveling salesman problem is to reduce the given cost adjacency matrix. So reduce the matrix in the sense we have to make sure that any one values in every rows should at least be 0, and any one value in every column should be made 0. So if the row values and column values are not 0, we have to reduce the given cost adjacency matrix. So for reducing the matrix, the first step is we find the row min, and then we find the column min, and then we calculate the cost of each nodes. So we have to find the row min. So in first row the minimum value is 2, in second row the minimum value is 3, in third row the minimum value is 1. We neglect the infinities. So the row mean values are noted here, and it's summed up, and the value is 6. 2 plus 3 plus 1, it is 6. After finding the sum, we perform row reduction. That is, every row values is subtracted with its minimum value. So infinity is written directly. 4 minus 2, it is 2. 2 minus 2, it is 0. The same way, second row the minimum value is 3. Therefore 3 minus 3, it is 0. Infinity is written directly. 4 minus 3, it is 1. In third row the least value is 1. So 1 minus 1, 0. 8 minus 1, 7, and infinity is written. So this is the result after row reduction. Now after performing row reduction, we have to perform column reduction. So in column reduction, we note down the least values in every columns. So in the resultant matrix of row reduction, we find the least values of every columns. So in first column the least value is 0, in second column the least value is 2, in third column the least value is 0. We sum it up and we make a note of it. It is 0 plus 2 plus 0, it is 2. So then we have to subtract the least values of every column with all its values. So it is 0. Infinity is written directly. 0 minus 0, 0. 0 minus 0, 0. In second column the least value is 2. So 2 minus 2, 0. Infinity is written. 7 minus 2, it is 5. In third column the least value is 0. So 0 minus 0, 0. 1 minus 0, 1. Infinity is written directly. So this is the resultant matrix after we perform column reduction. So this matrix we call it as the reduced matrix of node 1. So after finding the reduced matrix of node 1, we have to find the cost of node 1. So the cost of node 1 is sum of row min plus sum of column min. So it is nothing but 6 plus 2, which makes 8. So 8 represents the cost of node 1. So 8 represents the cost of node 1. It means that the person has to travel with the cost of at least 8, and the upper bound is said to be infinity, and this will be updated once we reach the leaf node. So here the number of vertices are 3. So from 1 initially I can travel to either 2 or 3. So as of now we found the cost of node 1, and the next step is I have to find the cost of 2 and then I have to find the cost of 3. It means that the cost to reach 2 from 1 and the cost to reach 3 from 1. So when I consider initially to find the cost of 2, its parent node is 1. So I have to consider the reduced matrix of node 1 as a given input. So the reduced matrix of node 1 is here, that is after we perform column reduction, the resultant matrix we call it as the reduced matrix of node 1. So this one is taken as the input, and having this as the parent node, I have to find the cost of node 2, that is C of 1 comma 2. So here if it is C of 1 comma 2, in the sense I have to make the first row and second column as infinity in the reduced matrix of node 1. So first row and second column, first row and second column is all made as infinity, and in addition to that we have to make 2 comma 1 as infinity. So 2 comma 1 is also made as infinity. So this is because I am traveling from city 1 to city 2, and if it is 2 to 1 means it makes a subtour. So in traveling salesman problem, subtour is not permitted. So we make 2 comma 1 also to be infinity. So making all those first row, second column and 2 comma 1 is infinity, the remaining values are filled directly. That is 1 is filled directly, no change, and 0 no change. Here infinity, there is no change. After making this, see to that the matrix, is it reduced matrix or not. So the matrix is said to be reduced matrix if any of its row values and column values are 0. If not, we have to make it as reduced matrix. So here in first row it is all infinity, neglect it. In second row the least value is 1, make a note of it. In third row the least value is 0, so 0. The sum of 1 plus 0 is 1. So after row reduction, I have to subtract the row values with its minimum values. So it is infinity no change, here infinity no change, infinity no change, 1 minus 1 it is 0, here 0 is the least value, so no change. So this is a matrix after row reduction. After we perform row reduction, we have to perform column reduction. So see here, in first column already I have one 0 value, in second column everything is infinity, in third column I already have one 0 value. So I need not perform column reduction, it is already reduced matrix. So this matrix we call it as the reduced matrix of node 2. And then we calculate the cost of node 2. So the cost of node 2 is calculated using C of 1 comma 2 plus R cap. It means that C of 1 comma 2 is nothing but we have to refer the reduced matrix of node 1. Why? Because node 2's parent node is 1. As of now we are calculating the cost of node 2 whose parent is 1. So the reduced matrix of node 1 is taken as the input here. So in this matrix 1 comma 2 value is 0. So that is C of 1 comma 2, it is noted as 0, and R is nothing but it is a cost of parent node. So for node 2 the parent is 1, so its cost is 8. Therefore R is equal to 8, and R cap is the reduction values. Here having this as the input, this is the reduced matrix, and to reach this reduced matrix we are subtracting the row min and then column min. So the row min values are 1 plus 0 1, and column mean value is 0. So 1 plus 0 plus 0, it is 1. So R cap, that is the reduction values are 1. So 8 plus 1 9, which makes the cost of node 2. So the cost of node 2 is 9. The cost of node 2 is 9. Here in this case, initially we have calculated the cost of node 1 as 8. So here also the formula is same. To calculate the cost of any node, it is the cost of one vertex to other vertex plus R cap, that is cost of its parent and the reduction values. Since we are calculating the cost of node 1 here, it itself is a parent node, so this will be 0, and R cap is the sum of reduction values. So that is what we have considered here. 2 plus 3 plus 1 and 0 plus 2 plus 0, it is 6 plus 2 8. So this is my R cap here, and cost of parent node will be 0 and cost of 1 comma 2 is here, whereas here I am calculating the cost of node 1 itself. So it is 1 comma 1, it is nothing, so it is 0. So 0 plus 8 plus 0, here it is 0. The same way here we calculate C of 1 comma 2 plus R cap, which makes 9. So this is the cost of node 2. Similarly, we have to find the cost of node 3 having 1 as the parent node. So here again we take the reduced matrix of node 1 as the input, and from that matrix we have to reduce the matrix to calculate the cost of node 3. So to find the cost of node 3, C of 1 comma 3, I am considering the reduced matrix of node 1. So here it is C of 1 comma 3. Therefore we have to make C of 1 comma 3. So therefore we have to make first row and third column as infinity. So first row is made as infinity and third column is made as infinity, and also we have to make 3 comma 1 is equal to infinity. So 3 comma 1 is infinity. So this is because to avoid the subtour issue. So first row, third column and 3 comma 1 is all made as infinity in the having a reduced matrix of node 1 as the input. Then we have to check if the matrix is reduced or not. So see to that, in every row I have 0 values. So here nil, 0 I have, and here there is no 0. So the least value in third row is 5. Then perform row reduction. So this can be performed by subtracting the row values with its minimum values. So it is infinity neglected, 0 row, already I have the least value, and third row the least value is 5. So 5 minus 5, it is 0. So this is the resultant matrix after row reduction. Then we check if the columns are reduced or not. So in first column I already have 0, second column I have 0, and third column is infinity neglected. So this is the reduced matrix of node 3. And then we find the reduced cost. So the reduced cost is 5 plus 0, it is 5. So this is my R cap value. Now to find the cost of node 3, I have to find C of 1 comma 3 plus R cap. So R is the cost of parent node. So the cost of parent node is here node 3. So the parent node is 1. So the cost of node 1 is 8, as we had seen here. The cost of node 1, the cost of node 1 is 8. So the cost of parent node here is 8, and R cap is the reduction values. So the reduction value is 5, and cost of 1 comma 3. So this has to be referred from the reduced matrix of parent node. So in the reduced matrix of node 1, it is C of 1 comma 3. So C of 1 comma 3, it is 0. So C of 1 comma 3 is 0. So 0 plus 8 plus 5, it gives 13. So 13 is the cost of node 3. So here we have calculated the cost of node 1 is 8, the cost of node 2 is 9, the cost of node 3 is 13. So among 2 and 3, the least is 9. So this is my least cost node, and this should be branched out further. So here in branch and bound technique, the nodes can be branched further based on breadth first manner, and it can be FIFO order, that is first in first out. First in first out in the sense, after calculating 1 I have to branch out to either 2 or 3. So initially I will branch out to 2 and then I will also branch out 3, whereas here this is least cost branch and bound. It means that among 2 and 3 I have to I'm branching out only the node 2. Why? Because this gives the least cost. So 2 is branched out further. So from 2 the only possibility is I can reach 3, since the given graph is having only 3 vertices, 1, 2 and 3. So from 1 2 is visited. Obviously after 2 I can branch out to only 3. If suppose this is the least cost, in the sense I'll branch out to 3 and I'll reach to 2. So here if I branch out to 3 I have to find the cost of node 3. So to find the cost of node 3 I have to consider the reduced matrix of its parent node as the input. So the reduced matrix of node 2 is considered. Since why? Because 2 is the parent of node 3. So this is the reduced matrix of node 2. We have noted it here. So this is the reduced matrix of So this is the reduced matrix of node 2. Infinities 0 0. So this is the reduced matrix of node 2, and that is taken as the input here. So this is the reduced matrix of node 2. So having this as the input, I have to find the cost of node 3. So to find the cost of node 3, it is C of 2 comma 3. So C of 2 comma 3 in the sense I have to make second row third column as infinity. So in this reduced matrix, second row and third column is all made as infinity, and in addition to that 3 comma 2 is also made as infinity. Why? Because it forms a subtool. So 3 comma 2 is also made as infinity. So second row third column and 3 comma 2 is made as infinity. The remaining values are filled directly from the reduced matrix of node 2. So this matrix should further be reduced. So make sure that any one value in every row and every column is at least 0. So here this particular row infinity, here it is 0. So if I consider the column, it is 0, infinity, infinity. So it is already a reduced matrix. Now to find the cost of node 2 to 3, that is to find the cost of node 3, it is C of 2 comma 3 plus R cap. So R cap is the reduction values. Since there are no reduction values here, it is 0. It means that I have not made a note of any row min or column min and subtracted it. It is already in a reduced form. So it is 0, and R is the cost of parent node. As of now I'm calculating the cost of node 3. So its parent node is 2. So the cost of node 2 is 9. So that is noted here, and C of 2 comma 3 is in the reduced matrix of node 2, it is 2 comma 3. So it is 0. So 0 is noted here. So 0 plus 9 plus 0, it is 9. So this gives me the cost of node 3. So C is equal to 9. That is the cost of node 3. Therefore we have covered all the vertices, that is from node 1 I am traveling to node 2, and this is branched out further to node 3, and since there are no more vertices, obviously the next node is going to be 1. That is the path is 1 to 2, 2 to 3 and 3 to 1, and the total cost is 9. So we can check the given input graph. From 1 to 2 it is 4, 2 to 3 it is 4, and 3 to 1 it is 1. So 4 plus 1 it is 9. So the cost of traveling from vertex 1 to vertex 1 via node 2 and node 3 is 9. So this is the traveling salesman problem using branch and bound technique, where we focus on optimization problem, and it is the process is done breadth first. the process is done in a breadth first manner, whereas in case of backtracking, we find the solutions in a depth first manner and we focus on finding all possible solutions. Whereas here in branch and bound technique, it is breadth first manner and we focus on finding only the optimal solution, and it is least cost branch and bound in the sense we branch out the node based on the least cost. If the cost of one node is lesser than the cost of other remaining nodes, only that particular node is branched out further. So this is least cost branch and bound. Thank you.